Hello, folks. I hope you're all doing well. This is actually the second time I've done this video because the first time, right at the end, when I was identifying the area of the face of a coil, I said that the area's units were meters per second instead of meters squared, which meant I'm having to do the entire video over again. So, under normal circumstances, I would do a demonstration for you. This is the beginning of the magnetic induction and Faraday's law lab, or not lab, but chapter. But I'm going to put that off until tomorrow. Right now, what I'm going to do is give you a quick little rundown on some math that you're going to need to be able to deal with. It's actually math that you've run into before. It's related to this idea of flux. In the past, when we were talking about electric fields, and the idea that you can have an electric field that permeates a space, and if you had a surface in that space, that some of those electric field lines would pass through that surface, and that a measure of how many field lines were passing through the surface would be measured by what's called the flux, the electric flux through the surface. We're going to be dealing with magnetic flux now. That's what's important here. And so you have here this magnetic field. The magnetic field is in this direction here, as you can see. This is supposed to be a coil. Okay, the coil bounds an area, which is referred to as the face of the coil. And that face has an area to it. So it's just sort of a preliminary observation. We could define a vector that's going to be perpendicular to this face and whose magnitude is equal to the area of the face. And in fact, we're going to do that, and we're going to call it an area vector. And you'll see why we want to do this in a second here. So think about this. This magnetic field line right here, it's going to have a component that's going to be in the plane of the face. And because it's in the plane of the face, it is not going to end up penetrating the face. It's not going to end up moving through the face. And so it is going to provide no magnetic flux through the face. There will be a component that is perpendicular to the face. It will penetrate the face. It will move through the face. And in fact, it will produce a magnetic flux through the face. So effectively what we need to do is we need to take the component of the magnetic field that is perpendicular to the face, which is to say the component that's along the line of A, and we have to multiply it by A. And that will tell us how much magnetic flux is passing through the face of this coil. Thinking back to the math that you learned, or that you've been using pretty much all year long, if you want the product of one vector and the magnitude of the second vector along the line of the first, that's a dot product. And so we have that the magnetic flux is equal to the dot product of the magnetic field vector and this area vector. This is the reason why we needed to define the area vector. Where the angle in the dot product is the angle between the line of A and the line of B. The units are Tesla meters squared. Okay, Tesla is the units for B. Area has got the units of meters squared. And this combination is referred to as a Weber, which is kind of fun. Anyway, so this is the PowerPoint that I pulled from the AP stack. I'm now going to go ahead and show you a couple of the PowerPoints that have come out of the stack from Ms. Dunham. And I'm not going to take a lot of time on this, but I just want to show you what's there. So she, here is her definition for magnetic flux. Here she has magnetic field lines. Here's a coil. Here's the area vector. So this is kind of the same kind of thing that you just saw. This is sort of nice. It's showing a magnet with magnetic field lines, fairly intense, coming right straight out and then dying off on the side. Here you have a coil that just has very little in the way of magnetic field lines passing through, so there's a low flux. Here there are more lines, so it's a medium flux. Here there are all sorts of lines. It's a maximum or a high flux. So this is kind of fun. Here are the magnetic field lines if you had a coil. So if I had a coil here, and I wanted to go ahead and put that coil in this field in such a way that I got a maximum flux, how would I orient the coil? So think about it. If you want to pause the video to think about it, go ahead and do that. Okay, hopefully you're back by now. That's the way you're going to orient it. That's going to allow for the maximum number of magnetic field lines to pass through the phase. What about the least? Think about it. Pause if you need to. Okay. That's going to orient in such a way that the magnetic field lines are going to pass by. None of them are actually going to go through the phase. Second question is really kind of fun. Argentina has more land area than Greenland, but it has, let's see. So why is the magnetic flux of the Earth's magnetic field larger through Greenland than it is through Argentina? So go ahead and pause, think about it. Okay, hopefully you're back. Solution, Greenland is closer to the magnetic poles. So here's the Earth. Here's Greenland up here. Magnetic field lines are coming in to the pole, so they're coming in pretty much perpendicular to where Greenland is, and you're getting a pretty good sized magnetic flux. Argentina is down close to the equator. Magnetic flux lines are passing by. I'm on the wrong side here, but magnetic flux lines are passing like so. So they're not passing through Argentina. They're sort of passing by Argentina. You get less magnetic flux. Kind of a fun question. Anyway, that's pretty much it.